The equilibrium associated with weak acids is controlled by Ka. The equilibrium associated with weak bases is controlled by Kb. Both very similar, both looking at slightly different things. Typical problem, though, would be one like this. You have a weak acid, the Ka of hypochlorous acid is, so if they give you the Ka, it's probably a weak acid. Just make sure they're giving you the Ka for the species that you're looking at. Ka of hypochlorous acid is 3.5 times 10 to the minus 8. Calculate the pH of a 0.075 molar solution. Very straightforward in that sense. So first we write our little reaction. HClO plus water dissociates into H3O plus and ClO minus, the conjugate base. Okay. Proton is transferred to make H3O plus, and the Ka for this is equal to ClO minus, H3O plus, and HClO. And they ask us to find the pH. Before we find the pH, we need to find H3O plus concentration. And luckily for us, we have an equilibrium statement and starting concentrations. Given an initial point, we can use estimates or algebra to figure out, predict amounts at equilibrium. So this is back from the previous chapter. So we can generate an ICE table, our initial value. 7.5 times 10 to the minus third. This would be 0 and 0. We start with the nominal concentration, assume that it doesn't dissociate. And then at equilibrium, minus x, x and x, and then the actual equilibrium values themselves, 7.5 times 10 to the minus third minus x, plus x, and plus x. And so we can plug those into our equilibrium statement. Ka is equal to x, 7.5 times 10 to the minus third minus x. Now, because this is a weak acid, we're going to assume that this value will be approximately equal to 7.5 times 10 to the minus third. X is small. Because it is small, this number minus a small number will be approximately equal to the same. And so, this becomes equal to 3.5 times 10 to the minus 8 is equal to x squared over approximately 7.5 times 10 to the minus third. And so we're left with this little bit of rearrangement to take care of the math. So this is 3.5 times 10 to the minus 8 times 7.5 times 10 to the minus third is equal to x squared. This gives us 2.62 times 10 to the minus 10th is equal to x squared. And so square root of both sides, 1.62 times 10 to the minus 5th is equal to x squared x, where x is equal to our H3O plus concentration. Once we have that, we just take that number, convert it into pH. That's the hydronium ion concentration, 1.6 log. pH is equal to 4.79. Given a Ka and a concentration, you should be able to measure the pH of a weak acid solution. Now, a weak base is not radically different. In a weak base, we have a weak base. In this case, we have ammonia in H3 plus H2O goes to NH4 plus OH minus. This is Kb. Kb is always the base reacting with water to produce the conjugate acid and hydroxide ion. know Ka, know the form of Ka, know the form of Kb for any given acid or base. This is just a written out expression for the Bronsted definition of what a base is. So too with the acid. This is a written out Bronsted acid definition with water acting as the acceptor or donator for the proton. So, once we have this, all we need is Kb, and Kb for ammonia is 1.8 times 10 to the minus fifth. It's given in the problem. What is the pH for ammonia? Well, knowing Kb, again, we look it up in the table, we find our table, we find our material, done. Once we have that, we set up an ice table, and I'm just going to write the equilibrium portion. So this is a 0.04 molar solution. A little bit of it changes. Some of it is formed into hydroxide and ammonium. And then we can set it in with a Kb. Now the difference here is that we are looking for hydroxide ion. Kb is equal to x squared times 0.040 molar minus x. And then the assumption is that this will be small. And so this becomes equal to 1.8 times 10 to the minus fifth is equal to x squared divided by 0.040 molar. Due to the small x assumption, allowing us to calculate x. 1.8 times 10 to the minus fifth times 0.04, 8.48 times 10 to the minus fourth. But remember, this x is equal to the hydroxide ion concentration, and we're asked for pH. There's two ways to go here. So I will convert this to POH, which would be, the POH would be equal to the negative log of 8.48 times 10 to the minus fourth, or 3.07. And then pH plus POH equals 14, and so therefore pH is equal to 10.92. Which makes sense. This is a base. This is a weak base. Because it's a weak base, the solution should be basic. 10.9 is a basic pH. Given any weak acid and the concentration, you should be able to calculate the pH. Given any weak base and the concentration, you should be able to calculate the pH. Or some surrogate for pH, hydronium ion, hydroxide ion, or what have you.